And just to give you an idea of what we can find, we can then have a look at what those yields were in the different fields. Obviously we are identifying the different crops that were obtained, and we're often getting 0.5 to 1 tonne yield variability in some of the fields. That's not unusual. Our soils are quite variable. We only have to travel about 100 metres before we can shift from one soil type to the next, which can introduce a range of constraints. And then, because we have classified the soil in each region, we are able to extract 3 measures. We have the actual yield that the farmer achieved, which we extracted off the yield model, the yield monitor off the harvester. We have the simulated yield, which is where we take the farmer's management and run the crop simulation model exactly using that management. And then we have water limited yield potential, where we put more inputs on if necessary to see how much yield we could grow. So in this context, that means simulating what more nitrogen would have done in terms of generating yield. To ask a very simple question, was the field nitrogen limited? And you can see here in this particular example, on zone A of this particular field, we have a 1.5 tonne yield gap, which is quite substantial. In zone B, where there are some soil constraints that we have identified, that gap is much lower. Because we have the soil chemistry, we can start exploring aspects of that. In this particular instance, we had very good levels of organic carbon by Australian standards. We had very high levels of phosphorus, and we had good availability of nitrogen. So there didn't appear to be any particular issue with soil chemistry. We are then able to go in and track the management of that particular field. And this is one of the interesting offshoots that we discovered that we never expected in this project. Despite having phosphorus levels that would have enabled the farmer to grow a crop without any phosphorus fertiliser at all, they have gone and applied 110 kilograms of DAP. This is something that we are now picking up. There is a lot of agronomic management coming through these records that does not appear to be essential or necessary. That surprised us. We are able to track the weeds and explore the diagnostics, but in this issue, in this particular field, weed populations were extremely low and would not have been doing anything to the yield. They would not have been the cause of the yield gap in this instance. Root health scores. The plants are all sampled, sent to a pathology lab where trained pathologists are then scoring the roots, and we are picking up root health scores. Anything above 2 suggests that we are getting damage to the root system that could be leading to a yield gap of some sort. We have the visual disease scores as well in other fields. So this is zone A and zone B. Oops. And again, we're able to explore whether the diagnostics of weeds changes from one zone to the next. Oops, I'm going the wrong way. Moving on from a paddock that does have damage. So basically the conclusion, that we had from that first paddock was that it appears as though there is a disease problem and a pathogen problem that is not being managed and now needs to be addressed. And that would be the explanation for the yield gap in that particular field. If we move to another field, we can see that this was a very high yielding field, achieving 6 tonnes, no measurable or discernible yield gap at all. There was no nitrogen deficiency. The farmer was able to achieve 6 tonnes. They were hitting yield potential. So our conclusion here could have been there is nothing wrong with this particular farm or this particular farming system, except, and this is where the yield mapping technology comes in, what portion of the paddock actually achieves these 6-tonne yields. What we can see is that by chance we happen to locate our transects in the highest performing part of the field. So we then had a field that is being uniformly fertilised and managed for 6 tonnes, yet the field average is only 4.5 tonnes. We are now seeing a very similar problem to what we saw in an earlier representation, where this particular farmer is putting the inputs on for 6 tonnes when they're only able to grow a 4.5 tonne crop on average across the field. Again, we have disparate extraction of phosphorus across the field, so this is giving us some indication that in some parts of the field the crop is not able to use all the inputs available, so we have wastage of resources to some extent. Again, there is plenty of nitrogen. We start exploring the complete suite of practices that were deployed into that particular field, and we can see large amounts of trace elements applied. We have multiple chelates, multiple applications of urea. We also have a reasonable range of herbicides applied. So what we have is a field where literally, if you can think of an agronomic intervention to apply, it has been applied. The farmer has not hesitated to do anything whatsoever. I went through this list and started drawing lines through things that I didn't think were necessary to still achieve that yield. I was able to reduce the cost of growing that field by about $150 per hectare for probably no yield loss at all. And again, this is another issue that has appeared just by inspection of the data. I haven't yet gone through this. I do machine learning algorithms and I'm used to that style of research as well and dealing with big data. But just a casual inspection has totally altered what we think we will do with these sorts of data that are coming in. Again, this field had reasonably successful weed management, an emerging population of ryegrass pointing to a future management issue, but 16 plants per square metre is unlikely to damage yield, particularly in a 6-tonne crop. What we are able to do, so moving on now, so what I showed you before is a breakdown of an individual field, how we would work through it with an agronomist. What we have developed is a reporting system to send that information back to a consultant linked to a farmer, so they get this information, so they get a feedback from the project. That system is still in progress, but we have beta versions that are currently being tested. But then there is the bigger issue now of we're now amassing a large data set. And this is the first thing that we start seeing, and we start to see this sort of distribution across almost every biotic constraint you can imagine. So we often get a large number of fields that have minimal constraints or minimal constraints to one issue. This is ryegrass populations. So 30% of fields have very low levels of ryegrass and weeds are being effectively managed. We start seeing increases in populations on a small portion, and then we have our outliers. This classic Poisson distribution, it's the first thing that scares any statistician if you are going to come at this with conventional linear mixed effects models. We can't go in and use GLMs on this unless we start accounting for these distributions. Not only that, because we are monitoring the fields multiple times through the year, we can now see what sort of weed populations we have at growth stage 65. We are now able to assess whether the farmer's weed management was successful and did they deal with that particular problem. So we're now looking at not only documenting the weed management strategy that was used, we are able to comment on whether the efficacy of that weed management was successful. So we are now able to track the emergence of herbicide resistance across the country through this particular monitoring regime just because we can say, well, how many weeds were there? You sprayed for ryegrass. You've still got a population of ryegrass after you sprayed for it. Our conclusion is that your herbicide did not work. Therefore, you have a resistance issue. How are you going to manage that moving forward? So this is the sort of inference that we can make from these sorts of data, and we are only starting to look at how do we analyse these data, how do we deal with these complex distributions, and what inferences, what agronomic inferences can we make. So we are increasingly talking to consultants one-on-one, presenting them with that sheet of information and drilling down into an individual paddock to make an inference as an agronomist would, and then stepping back and saying, how do we build a machine learning algorithm to represent the thought processes of an agronomist, to represent this process that I just described here, that simple thing of weeds now, weeds later, applied herbicide didn't work. That is not an analysis of variance. So how do we take our data science forward to get the learnings we need to communicate them to the agronomists, to give them a useful piece of management information as a result of being involved in this project? Oops. So we really, from our preliminary investigations, we've identified two contrasting management styles in Australian farmers. We have fear of failure. It's a risk-averse attitude to farming. It's too few inputs. It's not enough to achieve yield potential. This is perhaps quite common in the drier regions. There's been journal papers published where farmers are not putting on enough nitrogen. But this is the second one that I didn't actually anticipate going into this project. It's the fear of missing out. And that was that example of that other paddock I showed where there were too many inputs applied to the field because they just didn't want it to, they just thought they needed to. And given you have sales consultants whose jobs it is to sell fertilisers, it's not hard to imagine how this can, how this can unfold. And what we are interested in doing is identifying how common is this particular aspect of farming, because a lot of the way we talk about our research, the way we deploy economic models, really taps into this psychology of helping farmers justify why they should adopt a management technique. Does this process, this completely changes the way we should consider delivering research outputs. It's so different, it's not funny, and we haven't even thought about what do we do if we find out 50% of our farmers are putting on too many inputs and achieving yield potential. So they've ticked the yield potential box, but they've done it in a very inefficient manner. So I deliberately kept this fairly short, but we have a new survey that's establishing and understanding the basis behind the yield gap that has been identified. It is all about understanding regional insights and national significance, but doing it in a way that is scalable. We want to go from the sub-paddock level or sub-field level to the field level, to the district and region, to the nation. Importantly, all the information goes back directly to the farmer. Often when surveys have been conducted in the past, they've been written up in a report for a funding body and commented on weeds are a problem, disease is a problem, but they never delivered it back to the person who took the trouble to give them the information. We have invested enormous resources in correcting this deficiency. And obviously, it's creating an information resource for meta-analyses of all biotic stresses and production trends. So we'll be able to engage the statistical sciences, but again, as I highlighted, we are now challenging the fundamentals of those statistical sciences, what the philosophies are with the design and how we move forward. So thank you.
Yeah, I have a question on the feedback mechanism.
Sure.
How do you process the information? In which way do you process the information when you take it to the farmer? Or in which mechanism?
Sure.
So which mechanism do you take that information to the farmer, and do you evaluate farmers' adoption afterwards, after you have provided that feedback?
So that's a really good question. And at this stage, the mechanism is that a PDF of all the information we derived and some commentary goes to the consultant. So this is all done through consultants or extension personnel engaged with the farmer, and then they deliver that information to the farmer. How the consultants then use that information, we still don't know, because the project's only in its second year of operation, so we haven't had a chance to know whether they react to that information. But because this is a 5-year study, we go back to each of those points every year. We will know if a weed problem in year 1 still persists in year 2. If it does, that tells us that they are not reacting to the information provided to them by the consultant. So a lot of this is about building informatics using various statistical processes to make the deduction that you just, or answer the question that you just posed.
Thank you. It will be interesting to know also how to make this type of analysis useful for the farmer, sustainable over time.
Sure.
Because this is based on a very specific project, and how would it work afterwards?
Yep. Yeah.
Who pays the consultants?
We do.
Not the farmer?
No. Oh, sorry. The consultants are part of the farmers,
right.
but we have paid the consultants additional funds out of our research budget to do this work.
The main thing is farmers hire the consultants, right?
Yeah.
That's the farmers I know in Australia. They pay for these people.
Yes, they have to.
So, isn't there an obligation for these consultants to share information wherever it comes from and help the farmers do a better job?
No.
No.
It's a very interesting relationship, a very complex relationship between consulting industry and the farmers.
Okay.
There are some.
Worth the case study in its own right then.
Absolutely. This is one of the offshoots of this project that we never anticipated, and this is one of the things about new data sciences. We have inadvertently been able to evaluate how capable a consulting industry is of dealing with the data sciences. There are a percentage of consultants who are very capable of dealing with every aspect: yield monitoring equipment, variable rate technology, using apps in the field.
Yeah.
And then there is another percentage of consultants who struggle with the way agriculture is moving.
Okay, so that's a bit of a bell curve.
Yeah, yeah.
Nonetheless, so for the part that you pay them for,
Yeah.
these consultants, you have an agreement of what they're supposed to deliver, right?
Yes.
You do.
Yes.
Just checking.
They don't all, yes.
You mentioned the project has developed apps for data collection.
Yes.
Are any of those apps integrated into machine learning and?
Not yet. So I have another project that I'm involved in where we are starting to build apps that provide data for machine learning algorithms that update. So that's another whole area of work that I lead. But I haven't touched on that here. But yes, we are certainly moving down that path. Yeah.
Have you considered doing the yield gap analysis mid-season rather than at the end, so that it's at a stage where the farmer can still do something about it?
Sure. The only problem you've got with doing yield gap mid-season is you don't know what your yield is. So you can calculate yield potential. You can look at where the trajectory of the field is, and we are doing that. So we provide feedback on what we think the projected yield potential might be. but you don't have actual, so you can't calculate the gap halfway through.
Well, in our environment, NDVI, it's a very good predictor of final yield.
Yeah, it's not in Australia, and it's because of what Andrew talked about earlier. So the correlation between NDVI and yield across Australia is less than 0.3 because of terminal drought. And the end of, having said that, we do have other models that give us an idea of that process and do use NDVI, and we do have processes of taking remotely sensed information and performing model updating and that sort of process. So we are moving down that track, but that terminal drought makes it very hard.
Thank you.
Brent?
I find it interesting. I find it very interesting that some of your conclusions about farm advisors or technicians or technicians, however we call them, are very similar to what we see here in Mexico. So I think we should do some sociological study
I agree.
about that group of people, like any other product would do, and see if we actually are not trying to target a group with one solution or one product, but probably should have 3 or 4 different products coming from the same R&D stream, but another way to sell and package the same thing and make it work in their way of thinking.
Yep. It's the consultant-farmer relationship is extraordinarily complex because a consultant is essentially an employee of the farmer. I have good friends who I went through university with, obviously, who are in that industry, and they tell me things that about that process and about that relationship and how they operate quite differently with every different client that they have. Some farmers are looking for a support mechanism. Other farmers are looking for an advisor. It's the... Yeah, absolutely. Yes, exactly.
Just to get an idea, so how many farmers is one farm advisor or consultant?
They vary, but generally 30 to 40. 50 would be a lot. So one...
No, because they have large farms.
So one consultant could effectively be providing advice on 250,000 hectares. But it varies. There are different business models out there. So there are now consultants operating as separate consulting companies. So there'll be 10 or 15 consultants as part of that company, how they service those clients, what services they provide. They could be business consultants, banking consultants, agronomists. They all operate differently. It's very difficult to classify or define a normal system.
What would be the average number of visits to the field?
Oh, really good question. So, again, that varies on the level of service the farmer wants. There are some consultants, they just do field plans and don't walk into the field. One of the issues we have in Australia is that if a field is so large that the conventional idea of monitoring a field has disappeared. And you can't get a representative assessment of a field anyway. If the field's 200 hectares, it's going to take you a long time to do a legitimate sample of that field. So they just kind of walk in and make an assessment, and that's how it's done. And that's a good one. So that's why we're moving to sensors as fast as we can. It's the only way that we are going to be able to move forward. So we have sensors looking at soil water estimation, moving towards sensor-based nitrogen decisions. There are projects around all these issues, sensor-based weed detection, trying to think how do we get the sensors and the models to talk to each other to provide us a decision point. It's the downsides with being big.
Interesting.
Yeah.
may go to the States and you do all the learning and then we go.
Oh, we're making plenty of mistakes.
Yeah.
Yeah.
But it's interesting, it's a business, you know, the consulting, it's a business.
Yeah.
They're surviving.
Yes.
And so, obviously, the farmers are making enough money to be able to fund, to generate this business.
Oh, yeah. It's look, consulting to a farmer is not a big expense. Might cost them. So, consulting, it depends, but look, figures of paying 20, 30,000 a year to a consultant is not unusual, and nor is that considered a large expense. You've got farms with operating budgets of $2 million a year. Okay, so 30,000 out of 2 million. It just depends. It's on the scale. They're big business. They're not. But it varies state by state. So Western Australia has far more consultants than South Australia and Victoria. Western Australian consultants I know are paid more than those in South Australia and Victoria. Different, you know, it all depends on service required and what the local departments of agriculture did or didn't do. It's quite a complex concept. Anyway. Thank you. Thank you very much.